Talk about Rolle's theorem. Rolle's theorem is one of the theorems that we use to help us tie global behavior back to local behavior. And it says the following. It's one of these conditional statements. So there's an if part and a then part. It said if, and there's three conditions. F is continuous on the interval AB. F is differentiable on the open interval AB. And f of A equals f of B. So let's think about what picture we're drawing here, satisfying all these conditions, and maybe we can guess what Rolle's theorem is going to give us. So we're looking at a closed bounded interval AB. F is continuous on AB. So that means that when I can make my graph, it's going to be a connected graph. F is differentiable on the inside of AB, so that means it's going to be a smooth graph. There's going to be no sharp turns or corners. And f of A equals f of B. That means the graph starts and stops at the same altitude. So here's f of A equals f of B. So it's got to start here and end here, and you have to connect this with a smooth connected piece. So, maybe it wanders up a little bit, maybe it wanders down a little bit, and it gets back to here. So Rolle's theorem says under these three conditions, then there is at least one value C between A and B where f prime of C equals 0. So this value C is between A and B. It's an x value. And it's where somewhere in between the derivative is 0, which means somewhere in between we've got a horizontal tangent line. Okay? All right. Now, Rolle's theorem can be shown using a couple tools we have in the past. We're going to be using the extreme value theorem, and we're going to be using Fermat's theorem. And so here's the proof of it. So for the proof of it, we're going to assume everything here in the if part. Now, there is a trivial case we want to get out of the way first. It's possible that the function is constant all the way through. So if f is constant, then f prime of x is equal to 0 for all x in the interval AB. And so that clearly satisfies the theorem. So the theorem is true. So the real meat to this comes in assuming f is not constant. So let's suppose f is not constant. Time to invoke the extreme value theorem. We're assuming f is continuous on the closed bounded interval AB. Since f is continuous on the closed bounded interval AB, the extreme value theorem guarantees f attains a maximum and a minimum on the interval AB. Now, it's completely possible that one of the maxes or one of the mins happens at the endpoints, because we know that from what we've been doing, right? The maximum or minimum could happen at the endpoints. Since f of A and f of B are the same, one of those things, either the max or the min, must happen in the open interval AB, somewhere in between. right? Because the function values at the endpoints is the same. And the function isn't constant. So, in this case, the maximum's happening inside. In this case, the minimum's happening inside. Or in this case, the max and min are happening on the inside. But the fact that the function is the same at these endpoints means that we're in one of these cases. So this means, well, what does that mean? If we have a maximum or a minimum in the open interval AB, this means we have a local max or min in the interval AB. And now it's time to cite Fermat's theorem. Well, let's be specific here. So we have a local min in the open interval AB. Let's call it C comma f of C. So by Fermat's theorem, we know that if we have a local max or a min from of a function that's continuous in an open interval containing the local max or min, we know that the derivative is either doesn't exist there or it's equal to 0. But what are we assuming? We're assuming this function is differentiable everywhere inside the interval. So Fermat's theorem says f prime of c is equal to 0, and that's the point we were looking for. We have a local max or a min. It's differentiable at that local max or a min. So Fermat's theorem guarantees that the derivative is 0, and that's Rolle's theorem. Now, if we take a step back and think about what this means, I mentioned global behavior and local behavior. So globally, if I look at Rolle's theorem, and once again, these are the same. If I look here at the average rate of change, so if I look at the average rate of change, or the slope of the secant line through the endpoints, f of b minus f of a over b minus a. In the situation of Rolle's theorem, f of b and f of a are the same, so we get a 0 slope here. Rolle's theorem says that there's at least one point then in the open interval inside. There's at least one point in here where the instantaneous rate of change, the slope of the tangent line, is also 0. So what's happening globally over the entire interval is matched by what's happening locally at one point inside the interval, at least one point inside the interval. So this is a theorem that takes global behavior and matches it back to local behavior. And we'll see a more general version, well, it appears to be a more general version of this in the mean value theorem. So thanks for tuning in.